we would like to further generalize the chain rule. Now let's consider a function of two dependent variables, and each of those dependent variables is now a function of two independent variables. That means s and t are ultimately the variables that the function z has to depend on. What we're going to do now is let x and y be differentiable functions of two variables. And let's say they're defined on some set t in R2. If x and y are differentiable functions, that means all of these partial derivatives here exist. That's one of the conditions of differentiability. Now, we are going to take all of the outputs from those two functions, x of s and t, y of s and t, and we're going to put them into some other set. That set is going to be the set of inputs that I need for the function that I'm going to talk about. So let z be a function of these two variables, x and y, and it's going to be differentiable on some set d, and it's going to have these continuous partial derivatives, fx, fy, for all points in d. And so that means there's one more mapping where we take this and put onto the real line, the function f mapping it there. Now, z has two independent variables. And that means there are two derivatives that we want to consider, dz ds and dz dt, and they're partial derivatives. So by the definition of partial derivatives and using the result that we got from the previous video, what happens is that we fix one variable constant and then we differentiate with respect to the other. And from the chain rule result that we got for a single variable, what we'll find is that this partial derivative is now the derivative of z with respect to x, the derivative of x with respect to s, dz dy, dy ds. This partial derivative here, dz dx, dx dt, plus dz dy, dy dt. So this is the more general version of the chain rule. Now, using this can be a little bit cumbersome. You might want to think of it as follows. If I have a function of two dependent or intermediate variables, that means I've got to take derivatives with respect to each one of them first. And because each one of those, so these are the dependent, and because each one of those is a function of two independent variables, I now need to add in this layer. And what this is going to produce is a tree diagram. And that tree diagram says if you want the derivative of z with respect to s, you got to follow this through all the way in all the different paths that you can get to an s. And so that means there are these two paths, and that's going to produce the result that we see here. If you want to get to t, you've got to follow all the paths that'll take you to t. That gets us these two areas there, and that will match with that result. So the tree diagram can often be helpful for you if you need to visualize this. So we're going to go through an example of this. So let's say z is the function e to the xy tangent of y. X is the function s plus 2t. Y is the function s over t. If I want the partial derivative dz ds, that means I need dz dx, dx ds, plus dz dy, dy ds. dz dx is like saying take an x partial derivative of this expression right here. Now, with respect to x, this is a constant, so you can take it out. And that means I'll have tangent of y in the front, d by dx of e to the xy. This, I just need to use the ordinary chain rule from single variable calculus. The derivative of e to the something is e to the something times the derivative of the something. So this is going to give me a y, tangent y, e to the xy. Remember, the derivative of xy with respect to x is just the y. dz dy, take a y partial derivative of this expression. Here I need to use the product rule. There's no way around it. So what I'll get is the derivative of e to the xy with respect to y times tangent y plus e to the xy times the y derivative of tangent y. This is going to end up giving me chain rule again for this term, but this time I'll get an x in the front. So x e to the xy tangent y plus e to the xy, and the derivative of tangent is secant squared y. So these are the two terms that we are going to need when it comes time to computing the full derivative. The last part that we need is dx ds. Well, this is the s derivative of s plus 2t, which is just going to give me a 1, and then dy ds, which is the s derivative of s over t, which is just a 1 over t. So now I need to put this all back together. So this is now going to give me the following. I'll have a y tangent y e to the xy times a 1. So this is dz dx. This is dx ds plus x e to the xy tangent y plus e to the xy secant squared y times 1 over t. So this expression right here is dz dy, and this is dy ds. Now, unfortunately, we need to put everything in terms of the independent variables. So this means everywhere we see a y, we need to replace it with s over t. So the tangent and the other expression become like this. Here upstairs, we'll get an s plus 2t times s over t. And then this second term is going to give me an s plus 2t e to the s plus 2t s over t, tangent of s over t, and all of this stuff is going to give me another s plus 2t s over t, secant squared of s over t, and all of this is multiplied by 1 over t. So it's a big mess. We can try to simplify it, but we don't need to do that right here. Finally, dz dt is going to be similar bunches of partial derivatives. The only thing that will change is that the x and y derivatives are now going to be with respect to the other independent variable. This thing right here is going to be the t derivative of s plus 2t, which is a 2. This is going to be the t derivative of s over t, which is going to give me a negative s over t squared. So when I put everything back together, I'm going to have y e to the xy tangent y times 2 plus, there's a common factor of e to the xy that I'm going to take out, x tan y plus secant squared y over negative s t squared. When I plug all the s's and t's back in, I'll get s over t times e to the s plus 2t s over t, tangent of s over t. All of that gets multiplied by a 2 plus e to the s plus 2t s over t s plus 2t tangent s over t plus secant squared s over t, and all of that gets multiplied by this term. Definitely painful to write this out. Now, finally, this chain rule can be extended to any number of independent and dependent variables. If you thought it was messy before, it can get really messy in general. So if I have a function that's a function of 3 dependent variables, and each of these dependent variables is a function of 3 independent variables, holy moly, we've got a lot of mess coming up here. I'm not going to give you a specific function, but what I will do is talk about the tree diagram. So we talk about the dependent variables first. We have an x, a y, and a z. And each one of these is a function of 3 independent variables. So for example, if I wanted the partial derivative of w with respect to t, I would have to go dw dx, dx dt, plus dw dy, dy dt, plus dw dz, dz dt. And you'd repeat this for each one of the 3 independent variables.